at the tilt. I got a 90-day extension and I feel with guilt from things done and seen. The water from a bottle, mine from a canteen. At night I hear the shots ring, so I'm a light sleeper. Cost of life seems to get cheaper. Out in the desert with a street sweeper. The war is over, so said the speaker. With the fight suit on, maybe to him I'm just a pawn. So he can advance. Remember when they used to dance? All I wanted to do was dance.
Ladies and gentlemen, we're gonna start in 2 minutes. Please take your seats.
Under my thumb, the girl who once had me down. Under my thumb, the girl who once pushed me around. It's down to me. The difference in the clothes she wears down to me. The change has come. She's under my thumb. Under my thumb, the squirming dog who's just had her day. Under my thumb, a girl who has just changed her ways. It's down to me. Yes, it is the way she does just what she stole down to me. The change has come. She's under my thumb. It's alright. Under my thumb, Siamese cat of a girl. Under my thumb, she's the sweetest pet in the world. It's down to me. The way she talks when she's spoken to down to me. The change has come. She's under my thumb. Take it easy, baby.
What do we know? What do we even know about this particular place and moment in time? What lies behind these walls? Is it night or day? Is our side of the planet facing the sun? Or is it the opposite one? What's the temperature outside? Could it be too cold? Or maybe on the contrary, is it in fact too hot? What are these walls? Are these even walls? How do we know they are what they seem? We only see what we see, implicitly trusting our sight. We observe and conclude. We observe and learn. But how can we prove our observations aren't letting us down? And above all, how do we know that the process of learning is even possible? And here's the answer. Basic research is the source of most new ways of thinking about the world, proving the process of learning to be possible. Chemistry, physics, mathematics, and biology allow us to understand nature, describe the world around us using formulas and laws, paving the way for applied research. That's why it's so important to invest into these disciplines to create the necessary tools for tackling global socio-economic and ecological issues. This award was created to promote scientific progress, to popularize science and international cooperation. It will be awarded annually to 2 scientists in recognition of their breakthrough discoveries, outstanding innovation, and active work in promoting basic research. It is no coincidence that this prize was named after Dmitry Mendeleev, a true Renaissance man who possessed a wide range of knowledge, not only in the field of chemistry and physics, but also in the field of aeronautics, hydrodynamics, and meteorology. His discovery of the periodic law and the periodic table of chemical elements has changed the course of science. And this is a perfect example of how one man's discovery of a fundamental law of nature influenced and continues to influence all of humanity throughout centuries. And so, ladies and gentlemen, welcome to the first Basic Research Awards ceremony of the International Mendeleev UNESCO Russia Awards. Ladies and gentlemen, Ms. Shamila Nair Bedwell, Assistant Director General for Natural Sciences.
Madam Director General of UNESCO, Mr. Valery Falkov, Minister of Science and Higher Education of the Russian Federation, Excellencies, distinguished ambassadors, friends, scientists across the world, dear guests, ladies and information. It is my immense honor and privilege to welcome you all to this awards ceremony of the 2021 edition of the UNESCO Russia Mendeleev International Prize in the Basic Sciences. Today we are marking UNESCO's history by celebrating science, basic science, and honoring our commitments towards future generations to making science, more and better science, not for its technology, not for leisure, not even for health or longevity, but for the hope of wisdom, which our kind of culture must acquire for its survival, in the words of Lewis Thomas. And now, Excellencies, I have the pleasure to invite Madame Audrey Azoulay, Director General of UNESCO, to please come on stage. Thank you, Director General.
Good evening. Welcome. Honorable Minister of Science and Higher Education of the Russian Federation, dear Valery Falkov, Mr. President of the Russian Academy of Sciences, Mr. Secretary General of the National Commission, Excellencies, Ambassadors, dear laureates of the UNESCO Russia Mendeleev International Prize in the Basic Sciences. I am very happy to welcome you to this ceremony today at UNESCO's headquarters in Paris to award the first UNESCO Russia Mendeleev International Prize in the Basic Sciences, a prize that comes at a very opportune time. The last 18 months have reminded us in pain how science and research can change our lives in important ways. If we have been able to save millions of lives, or to gather in this room tonight, it is thanks to the world's scientists, biologists, chemists. Working in record time, they developed and shared new knowledge of the virus and manufactured vaccines. We owe much to the basic sciences, to this fundamental human curiosity, which stands in awe of nature and attempts to understand it better. Looking beyond vaccines, which we have known about since Édouard Jenner and Louis Pasteur, this pandemic has shown us how necessary it is to build real confidence in science. This can be achieved through science education, of course, especially for girls. You know, it's one of our priorities here at UNESCO. But it can also be achieved by acknowledging the brilliant minds that crack the world's codes and drive forward scientific progress. And that is precisely the goal of this new prize, to celebrate great scientists and their discoveries. Today, we are honoring two exceptional scientists, two laureates who were announced at the beginning of this month of November, Professor Vincenzo Balzani and Yuri Oganessian. They are the worthy recipients of the first edition of this prize, supported by the Russian Federation, which I would like again to thank. The Minister just reminded me that this year has been proclaimed as the year of science and technology in Russia. Here again, a very opportune moment for this prize. In awarding this distinction, we're also paying tribute to the remarkable Dmitry Mendeleev, whom you remember, dear ambassadors, we celebrated at UNESCO during the International Year of the Periodic Table in 2019. Excellences, Mesdames et Messieurs.
Excellencies, ladies and gentlemen, this prize is named after Mendeleev because he is the very embodiment of scientific spirit for at least three reasons. First, his insatiable curiosity. His research focused on chemistry, but also, as we mentioned earlier, meteorology, hydrodynamics, and he even developed the first icebreakers. He is from a long line of remarkable Russian scientists, alongside Mikhail Lomonosov, Alexei Krylov, and Yuri Gagarin, who first flew into space 60 years ago, inspiring a passion for science among so many. Secondly, he had great trust in scientific cooperation. In fact, he saw the empty boxes of his famous periodic table of elements as opportunities for others to conduct research and to engage in collaboration. And since then, 55 new boxes have been filled in, and several of them have been thanks to your research, dear Yuri Oganessian. In recognition of your role, you have been awarded the honor of having an element of the periodic table, which you helped to discover, named after you. This places you in the very closed circle of scientists who have won this prize, but also whose names have appeared in the alphabet of matter: Pierre and Marie Curie and Albert Einstein. Lastly, we wanted to pay tribute to Professor Mendeleev because, as the Russian chemists Dmitry Mustafin and Natalia Tarasova wrote in the UNESCO Courier in 2019, he revolutionized the idea of what we now call sustainable development, which is a major issue for us at UNESCO. He was already calling for us to manage natural resources in a more rational manner. He was already advocating back then the need to deepen the link between science and society. And, dear Professor Vincenzo Balsani, allow me first to wish you a very happy birthday. It's your turn now. You have extended this legacy with your remarkable work on photochemistry reactions. Your work allows us to do what nature does through photosynthesis, converting solar energy into chemical energy. This work opens up major possibilities to address some of the major challenges of our time, which we've seen mentioned time and time again at the COP26, that is to phase out fossil fuels by harnessing the extraordinary potential of the sun. But your work is also an intellectual pursuit because you place the social role of science at the heart of your work. You've dedicated a number of publications to how scientific research can help us to achieve the Sustainable Development Goals and build peace. Excellencies, ladies and gentlemen, Aristotle once said that the beginning of all science comes from astonishment. This is the motto that we wanted to embody through this prize, which was initiated by the Russian Federation. By showcasing outstanding scientists, this prize allows us to reward them, but also to foster astonishment and curiosity and inspire other research as well. I'm sure that your work, Professor Oganessian, Professor Balzani, will be a source of wonder and may even inspire young people and young girls. That's one of the main goals of this prize, and I believe it's the most beautiful tribute we could pay to Dmitry Mendeleev. I would therefore like to congratulate you once again. You're awarded this prize at a very special time, the 75th anniversary of UNESCO and the General Conference, which has a very comprehensive and strategic scientific component with two issues which will be addressed this week: the recommendation on open science, which focuses on cooperation among scientific sectors and interdisciplinarity. A second recommendation will be presented tomorrow on artificial intelligence. I'd therefore like to thank all of you, including Russia, for your participation in the negotiations over the past 18 months as part of this ambitious project. It's thanks to the work of scientists, professors, promoters of science, international cooperation, as we can see at UNESCO, that we're able to breathe life into Mendeleev's ideal, which is also shared by UNESCO, building on rationality as the common language of humankind. Thank you once again.
Thank you, Madam Director General. I'm now honored to invite His Excellency, Mr. Valery Falkov, the Minister of Science and Higher Education of the Russian Federation, to please come on stage and to deliver his speech. Thank you, Minister.
Much esteemed General Director, honourable members of the jury, honourable laureates, dear award ceremony guests. On behalf of the Russian Federation, I welcome you to this award ceremony, where we will be awarding the UNESCO Russia Mendeleev International Prize in the Basic Sciences. I thank UNESCO and my French colleagues, and also all the organisers, for making it possible to hold this ceremony in person. I would particularly like to thank the eminent International Prize jury. Today's event is special because this year we are awarding the prize for the first time, and it is also the 75th anniversary of UNESCO. It is also symbolic that the ceremony is taking place in 2021. Because this year, the Russian Federation and our president has announced 2021 as the Year of Science and Technology. Science has always been a key national priority for Russia. The challenges posed by the COVID-19 pandemic, which all countries are facing, have demonstrated its immense importance. In this connection, the agenda for this year's Year of Science and Technology will focus on popularizing science and on attracting young talent to academic science. Today, we are holding the ceremony in the UNESCO HQ. Now, the authority and status of UNESCO, which has developed over the full 75-year history of this key international organization, cannot be overestimated. UNESCO is successfully adapting to new challenges and is having a positive influence on the development of a peaceful agenda in its areas of work. Russia fully shares UNESCO's ideals and accords utmost importance to all of UNESCO's work in cooperation with the organization. In this cooperation, science plays a particularly important role. In the international arena, we aim to actively strengthen scientific and technical cooperation with all states. Russia has always paid particular attention to basic sciences. These sciences require labor-intensive work, and they do not give quick results, but they form the basis, nonetheless, of innovative developments and contemporary technology. Behind each invention, there is scientific courage, there is creative zeal, and investigative enthusiasm, either of a single scientist and scientific collective or of international collaboration of a group of scientists. Knowledge is a powerful force. It allows humanity to make progress and to respond to contemporary challenges that face all our civilizations. It also helps us to resolve shared issues to improve the lives of billions of people. The large-scale organization in 2019 across the globe of events dedicated to the 150th anniversary of the periodic table of the elements helped us to develop cooperation and step up cooperation in terms of the exchanges between scientific personnel. This is clear if we consider that we began the year in Moscow and Paris, and we finished our Year of Science in Tokyo. Moreover, the Year of Science and Technology attracted more than 100 countries, and it resulted in the creation of this UNESCO Russia Mendeleev International Prize in the Basic Sciences. Russia wishes this prize to become significant and renowned across the globe. This has been achieved first thanks to our competent and authoritative jury, which includes Nobel Prize laureates and leading Russian and foreign scientists in various fields. I would like to express particular gratitude to these colleagues for their meticulous and difficult work in assessing and choosing between the entrants. The biography of a scientist can be seen as a long road towards truth, towards enlightened progress. Each step of the way offers new opportunities, new discoveries for the future. Today, in the light of contemporary achievements in science, the contributions of Dmitry Mendeleev have taken on new ground. They're gaining new ground, and they can be appreciated in all their excellence. The time has come to rigorously select from the various creations and discoveries of humankind. In this sense, the discoveries of Mendeleev are still very important and becoming even more so. This prize is also unusual in the sense that it is multidisciplinary. Nowadays, all the sciences are closely connected, and sometimes it is difficult to say to which science a particular discovery belongs. The prize is also special in that it pays special attention to and is aligned with contemporary trends and developments. I would like to congratulate the laureates of the prize, particularly Professor Vincenzo Balzani and Professor Yuri Tsolakovich Oganessian, one of our eminent compatriots. I also would like to say a happy birthday to Professor Balzani. I consider that the prize is a worthy recognition, professors, of your contributions, and that your brilliant contribution to the progress of humanity will be a beacon for new generations of scientists and academics. Without any doubt, this ceremony is only the beginning. It is a first step that will lay the foundations and will, I hope, become a solid tradition for honouring great scientists and our contemporaries. But much work lies ahead. Next year, the ceremony will take place in Russia. I hope that the pandemic will not spoil our plans, and I'd like to take this opportunity to invite all of you, dear friends, to take part in the second ceremony. We would be delighted to see all of you in Russia next year. I thank you very much for your attention. I wish you all fruitful work, breakthrough discoveries, and much success in your scientific work. Thank you.
The 7 eminent members of the jury of the prize were appointed in February 2021 by the UNESCO Director General for a 2-year period, renewable for a maximum period of 6 years. These members are Jean-Pierre Sauvage, France, 2016 Nobel Prize in Chemistry, CNRS Director of Research Emeritus, Professor Emeritus, University of Strasbourg, Distinguished Visiting Scholar, Northwestern University. Sir Tom Blundell, United Kingdom, President, UK Science Council, Chair, Biotechnology and Biological Sciences Research Council, Emeritus Professor and Director of Research, Department of Biochemistry, University of Cambridge. Grigory Vladimirovich Trubnikov, Russian Federation, Director, Joint Institute for Nuclear Research, Member, Russian Academy of Science, Member, Scientific Council for Nuclear Physics, Ana Maria Cheto Krames, Mexico, Research Professor, Institute of Physics, Lecturer, Faculty of Sciences, Director, Museum of Light, National University of Mexico. Tasuko Honzo, Japan. Shared the 2018 Nobel Prize in Physiology or Medicine. 2016 Kyoto Prize in Basic Sciences. Deputy Director General and Distinguished Professor, Kyoto University Institute for Advanced Study. Director, Center for Cancer and Immunotherapy and Immunobiology, Kyoto University Graduate School of Medicine. Tebelo Nyokong, South Africa. 2009 L'Oréal UNESCO Awards for Women in Science. 2015 UNESCO Medal for Contribution to Development of Nanoscience and Nanotechnologies. Distinguished Professor, Rhodes University. DST NRF Research Professor of Medicinal Chemistry, Nanotechnology. Director, DST Mintech Nanotechnology Innovation Center. Samia Chafi Kadour, Tunisia. Director General of Scientific Research, Ministry of Higher Education and Scientific Research. Member, C13 Commission, Physics for Development, International Union of Pure and Applied Physics. Member, UNESCO Open Science Advisory Committee established in 2020.
Excellencies, ladies and gentlemen, the chair of the jury of the UNESCO Russia Mendeleev International Prize in the Basic Sciences was unfortunately unable to join us here tonight. However, he has sent a special message for this ceremony. I'd like to now invite you all to listen to Professor Jean-Pierre Sauvage. Thank you.
Good evening, everybody. Well, let me first thank the Russian Federation and UNESCO for creating the Mendeleev Prize, Mendeleev being one of the greatest scientists since the 19th century. I would like to compliment the two laureates, Professor Vincenzo Balzani and Professor Yuri Oganessian. They have done fantastic discoveries, and I'm absolutely convinced that they were the two best scientists to be awarded this prestigious prize. So congratulations, very, very sincere congratulations. I'm happy of what the jury decided to do and to select you both in particular. Let me also say a few words for Vincenzo Balzani, whom I know for probably more than 40 years or so. I know that today is a special day for him, so let me say, Vincenzo, buon compleanno e auguri. So thank you very much for listening to what I had to say, and I wish you a great celebration. Thank you.
Merci beaucoup, Professor Sauvage. Excellencies, ladies and gentlemen, music and science are universal languages. It is therefore in honor of the two laureates of the UNESCO Russia International Mendeleev Prize for Basic Sciences that we have two compositions by two contemporary composers from Italy and Russia who will be performed tonight. We will begin with Lamentatio by the Italian composer Giovanni Sollima. Thank you. Excellencies, ladies and gentlemen, I'm now honored to invite to come on stage Professor Grigory Trubnikov, member of the jury of the UNESCO Russia Mendeleev International Prize in Basic Sciences. Thank you. I would also like to invite our first laureate to join us, Professor Vincenzo Balzani. Thank you. Thank you. Ladies and gentlemen, Excellencies, we'll now listen to a performance of the Russian composer Nikolai Sivchuk, which is called the Mountain Lullaby in honor of the second laureate. Thank you.
Thank you.
Excellencies, ladies and gentlemen, I'm now honored to invite to come on stage Professor Anna Maria Seto Kremes, who was the vice chair of this eminent jury of the UNESCO Russia Mendeleev International Prize in Basic Sciences. Thank you, Professor Maria. I would also like to invite Professor Yuri Oganessian, our second laureate, to please join us on stage. Thank you. Thank you. How are you? It's good to see you. Thank you. Thank you for coming. Please.
It was good to say a few words.
Madame la directrice générale, je vous demande.
Madam Director General, I would like to reassure you that my presentation this evening will be in English, which I think will be easier for everyone to understand.
Madam General Director, I would like, of course, to thank you, because this evening I am receiving such a wonderful, eminent scientific prize. I would also like to thank the jury for recognizing my work. Thank you very much. I thank you from my heart. Now, I have the feeling, however, that there's something else taking place in connection with this prize ceremony. The great mission of UNESCO, which demonstrates the spiritual and scientific development of our society. And this is a very important component. It is very important to pay attention to basic sciences and their importance. This is an excellent sign that UNESCO is paying attention to the basic sciences. The United Nations declared some time ago that 2019 would be the year of the periodic table. I was surprised how many people took place in the associated events and how much knowledge they had and how interested they were by these events. And now UNESCO is taking a similar step and is now allowing people to speak here on the stage about science and to receive a prize dedicated to the basic sciences. This is extremely important, and I congratulate you, Madam Director General, and all the people who have been behind organising this prize. Thank you very much.
Congratulations. Merci. Merci à vous. Merci beaucoup. Thank you. Excellencies, ladies and gentlemen, I'd like to invite our distinguished guests to join us in a group photo, please, up on the stage. I'd like to invite the Director General, His Excellency Minister Falkov, Professor Balzani, please, sir, Professor Sergeev, Professor Seta Kremes, Professor Trubnikov, and Professor Sharfi Kadur, to please join us in a photo session. Thank you. And we're going to hear a few words of Professor Balzani first. Thank you.
1, 2,
Yes.
1, 2, 3, go.
And Professor Oganessian to please join us. Please, sir.
We have a presentation.
Okay, so maybe we do the photo shoot and then you make your
Okay.
presentation. Professor Balzani wants to make a presentation to us, so maybe we do a photo shoot, please. Thank you.
Is that a me? Oh yeah, the way she talks.
One, two, 3, go.
Thank you all. I will have the honor now to invite Professor Balzani to deliver his lecture. Thank you, Professor Balzani. We have you.
Good evening. Director Azoulay, Minister Falkov, President Sergeyev, authorities, foreign and Italian colleagues, ladies and gentlemen. I'm very honored to receive the UNESCO Russian Mendeleev International Prize on Basic Researchers. As you know, this award was created in 2019 to commemorate the remarkable scientific heritage of Dmitry Ivanovich Mendeleev in the occasion of the anniversary of the periodic table, which is now which is the most brilliant idea in the history of science. Okay. In my talk, besides Mendeleev, I'd like to celebrate another outstanding scientist who has strongly inspired my own scientific research, Giacomo Chamichan, universally known as a pioneer of photochemistry and a prophet of solar energy. Now, Chamichan attended the International Congress of Applied Chemistry in the United States and presented a very important paper entitled The Photochemistry of the Future, that was published on Science. As some of you may know, this is really an outstanding paper in which Chamichan forecasted and discussed the possibility to replace coal, that was the only fossil fuel used at that time, with artificial photosynthetic processes powered by solar energy. In the following years, coal was progressively replaced by gas and oil, fuels much easier to use and apparently not so dangerous to health and environment. With the availability of such cheap and abundant fuels, nobody was anymore interested in solar energy conversion. The idea of an artificial photosynthesis was reconsidered much later after the energy crisis of 1973, caused by, as you can recall, the oil embargo applied after the Arab-Israeli war. In 1975, in a paper published on Science, we suggested to produce a clean fuel, molecular hydrogen, by water splitting using sunlight. Later, we elaborated and proposed a general scheme for artificial photosynthesis, and we developed components for this type of process. In particular, we developed multi-chromophoric system and tender system of light harvesting. Then we moved to supramolecular chemistry and supramolecular photochemistry. We organized 2 NATO workshops, inviting also colleagues of the Eastern Europe, a rather peculiar initiative at that time. And we succeeded to have with us scientists from East Germany, Russia, Poland, and Czechoslovakia. In these workshops, we discussed on chemistry, of course, but also more generally on the important role of science for building friendship and peace. Now, let me go back to the periodic table that deals with the electronic structure of atoms. We chemists, however, are dealing with molecules. Nevertheless, we are deeply interested in the periodic table because the differences among the electronic structure of atoms imply differences in the structure and the reactivity of their molecules. This is particularly true, as we will see, in the case of photochemical reactions. Now, when a photon of suitable energy is absorbed by a molecule, an excited state is obtained. The electronically excited state, because of its high energy content, is a transient species that must undergo deactivation. And the activation may occur essentially, it's not complete. Essentially in 3 ways: a chemical reaction, luminescence, and radiationless deactivation to the ground state. The excited states are characterized by some important features. First of all, an excited state is always has always a lower ionization potential and a higher electronic affinity than the ground state. And therefore, the excited state is always both a better reductant and a better oxidant, which is very important for chemistry, this one. Another very important characteristic of excited state is the lifetime. The lifetime of an excited state depends, of course, on the deactivation processes, these concurrent deactivation processes. When these processes are slow, the excited state's lifetime is long, and the excited state has a chance to go around in the solution to encounter other species and to give rise to energy or electron transfer processes. The chance of energy or electron transfer, of course, is much higher if the second molecule, molecule B, is already close to the excited state. This happens, this is important for us, in the so-called supramolecular multi-component systems, in which molecule B is linked by some type of chemical bond to the excited state. We have investigated the photochemical properties of several transition metal complexes and lanthanide complexes, and we have found that atoms that are close in the periodic table may exhibit quite different photochemical properties. Consider, for example, these 2 atoms, iron and ruthenium. These two elements have very similar properties. They give rise to plus cations that can coordinate to bipyridyl to give these two complexes. And these two complexes in the ground state have very similar properties because they have the same electronic configuration. But in the excited state, the two complexes have different electronic configuration, and therefore they have different properties. For example, the lifetime of the ion complex is only 1 nanosecond, whereas the lifetime of the ruthenium complex is 1,000 times longer. For this and other reasons, this ruthenium trisbipyridyl complex has several advantages concerning the possibility to undergo photochemical reaction. And it is indeed an ideal molecule for processing light signals. These are the spectroscopic and electrochemical properties of this complex. Here we have the absorption spectrum and the emission spectrum, and this is the reversible redox behavior. For this reason, it does. I'm sorry, but it was not my computer, so it is not possible to understand this part. Okay. Anyway, now, as everybody knows, in the last 30 years, there has been a race toward miniaturization of devices for information processes. In the hand of physics and engineers, miniaturization is conceived as a top-down approach to reach micro and possibly nanostructures. We thought that nanostructures could be more easily constructed by a bottom-up approach, starting from molecules. And indeed, the bottom-up approach, starting from molecules, is very flexible, and we can start from molecular components, appropriately designed. Components have specific properties. We can assemble this compound by self-assembly or design and synthesis. We obtain these supramolecular systems, which, thanks to the collaboration, so to say, the integration of the properties of the molecular components, we can display new properties and perform a specific function. Now, supramolecular chemistry has also other names. It can be called molecular level engineering because it can lead to molecular devices and machines, nanometer dimension. And it can also be called nanotechnology because nanotechnology as according to the definition given by Roll Hoffman, is the marriage of the synthetic talent of chemists with device-driven ingenuity. In recent years, indeed, many chemists began to work like engineers. To make macroscopic devices, an engineer designs suitable components and then assemble them in an appropriate sequence. Chemists can do the same. The big difference is that engineers work with macroscopic components, whereas chemists work with molecular components. And as discussed in our book, Molecular Devices and Machines, we can distinguish devices used for signal processes and systems capable of mechanical movement. Therefore, they can be called machine. For time reason, we show you only a few examples of molecular devices and machine. The next slide shows a molecular wire. As you can see, it's 4.2 nanometer long. And in this case, if we excite the ruthenium complex, we can obtain emission for the osmium complex. That shows that energy is transferred through this wire. Energy transfer among different molecular components can also be used to construct other types of devices. For example, we have prepared large multichromophoric dendrimers like this one, 5 nanometer dimension, made of 43 molecular components. The light absorbed by the peripheral units transfer energy to the intermediate and then to the core, which exhibits emission. As we have seen above, the purpose of our research on dendrimers was related to the possibility of construct a multichromophoric system to be used as antenna system for artificial photosynthesis. But after having published a couple of papers concerning dendrimers on the Journal of American Chemical Society, I got a letter from the US Department of the Army inviting me to attend a meeting on dendrimer technology and its potential military application to the US Army. I did not go. My answer was that I did not intend to contribute to military applications by means of my research. Now, let's see some other devices. Plug and socket are well-known devices in the macroscopic world. To make a plug-socket system at the molecular level, we have used this crown heater as a plug, and this other component, the socket. And we have used, let's say, acid-base interaction to assemble them. And we have seen that the excitation of the plug, so to say, leads to emission from the socket, as it happens in the macroscopic devices. Now we have also tried to mimic at the macroscopic, at the nanometer level, this kind of device, macroscopic device, which is in the first line. And so we have taken molecular components which have characteristics suitable to be associated. And in the associated system, we see that excitation of the ruthenium compound leads to electron transfer to the third compound. Assembling, disassembling is caused by, okay. Now, we have also assembled molecule like that, in which we have 3 connected threads, each one containing 2 different electron acceptor units. And then we have also synthesized these particular 3 donor rings. After assembling, we can something like that. We can put at the end of each thread a bulky group to prevent dissociation. Now, the next slide shows that we are in the nanometer range. This is the CPK model, and here we have a schematization of this system. Now, in this compound, if we add a base, the 3 ammonium stations are deprotonated. The interaction with the 3 electron donor ring ceases. Therefore, the platform goes down to allow the ring to surround the other weaker electron acceptor. Now, by addition of an acid, it is possible to go back. So this, in some way, was called a molecular lift. But it doesn't work here. Okay, but okay. This is anyway a molecular machine powered by chemical inputs. Then we have considered the. Okay, now it works. Okay, you can see that. Indeed, the platform does not go down altogether, so it's not a very good lift, actually. So these are the well-known rotaxane. and in which there are two different sides for the ring. Initially, the ring surrounds the station which offers the strongest interaction, which is the blue one. Then, by an external stimulus, it is possible to deactivate the interaction of the ring with the strongest station. And as a consequence, the ring moves to the other station. By a reverse stimulus, we can also go back. To move the ring back and forth, we need energy. And in most cases, the energy used was chemical energy, let's say redox or acid-base reaction. We tried to, we have designed and constructed a system like that, in which we have used solar energy to control the back and forth movement of this system. And so it works like that. We have put in the system the ruthenium pyridine compound, which is able to absorb light. After light absorption, this complex emits an electron. And the electron goes, the electron has to go somewhere, and it goes to the blue station, which is the best electron acceptor. But when the electron arrives at the blue station, the ring is not happy about that, so moves to the other station. And then it can go back. I'm sorry, but most of the slides are not. Now, this is a schematic representation of what happens in this system. We have that doesn't work. Sorry about that. Okay. Anyway, so let me go on and say that to finish, that in our, okay, now it goes. In our book on molecular devices and machines, we did something quite unusual. After having described it in 16 chapters, the scientific and technological aspects of this field, we have added another chapter, the 17th, as a final chapter, in which we discussed the role of science in our time. The reason why we decided to write such an additional chapter, I explained it in this introduction. This book deals with science, mostly with basic science. Therefore, it could, some readers will say it should, have ended with the previous chapter. But nowadays, can science be treated as a separate, neutral, and aseptic item? Can a scientist ignore the problems of the human society and isolate himself in an ivory tower? We believe not. We believe that there is a great need to debate the role of science and scientists in our society, and that a scientific book offers an opportunity. There should not be missed about that. So the reason why we decided, okay, so we need to recall in this chapter, we discussed topics that are not discussed usually in scientific books. We did that to recall first to ourselves and then to our colleagues that the social responsibility of scientists. Scientists must be carefully controlled that science and technology are used for peace, not for war, for preserving the planet on which we live, not for destroying it, for reducing, not for increasing the gap between developed and undeveloped countries, and for alleviating privileges, not for maintaining it. Of course, all of us agree on this concept, but perhaps we do not discuss them enough with our students. And maybe we do not talk enough with citizens who would like to receive a clear message from scientists. It is time to do that. I'd like to finish showing this beautiful image. As you can walk, it's about teamwork. Snowflakes are one of the nature's most fragile things, but just look at what they can do when they stick together. I'd like to use this image to thank the many people who surround me with affection, starting from my family, of course, and special thanks go to my colleagues and students who have worked with me over the years with great passion and enthusiasm, and also to the foreign and Italian colleagues whose collaboration was essential to obtain the results that I have summarized in my talk, as well as other results that I could not mention for time reasons. Thank you.
Thank you, Professor Balzani, for your very impressive and inspiring presentation. At a time where we're all grappling with climate change, photovoltaics, photosynthesis, sunlight is essential in our lives. Allow me also to express our gratitude for your approach to science as a tool for peace. Excellencies, ladies and gentlemen, I have great pleasure now to invite Professor Yuri Oganessian to deliver his keynote lecture. Thank you, Professor, for joining us on stage.
Ladies and gentlemen, the science we are doing are very old. From Democritus up to the great Dalton, people believe that all material world consistent from small bricks, he named these atoms, which interacted with each other in deep vacuum. Dalton supposed and identify that these bricks is elements. 36 elements were known at that time as 36 letters of the alphabet, which may describe of the material world. But 50 years later, Mendeleev in his work shows that atoms are not the building bricks because they have an internal structure. This structure was based for periodic law. 63 elements was known at that time. Indeed, that was later discovery of Henri Becquerel and their Pierre and Marie Curie, like radioactivity, like a nuclear transformation, and finally, in 1911, Ernst Rutherford proposed his very well-known model of planetary type atoms. We may really say that the birthday of the nuclear physics was in 1911, when was discovered a nucleus and electron around. Now we would like to understand where is the limit of existence of such system like a nucleus, where is the limit for electronic structure of the atom, and how is behavior of outmost electron, which is responsible for the chemical properties. Coming back to the nucleus, I would say that the first theoretical model of the nuclear matter, a nuclei itself, was made by George Gamow, a Russian scientist, in 1928. he identified a nucleus like a drop of the liquid with enormous density, and according to the theory of Gamow, which works at that time very well, a nucleus with atomic number more than 100 may not exist. Let's discuss this problem. It may or may not. And let me show you how we make artificial elements. The history is start in 1940, when American scientist makes a first artificial element, neptunium and plutonium, using the light particles like neutron and protons, and in this way they make several new elements up to the fermium. Fermium is element number 100. My personal career was started in 1963, when this method does not work to make a new element. We have to make some new one. It was completely changed the approach to artificial synthesis of elements. Instead of neutrons or protons, very light projectiles, we used more heavy ion like oxygen, neon, and the first element, which was very hard to produce, but nevertheless made at Dubna in 1963, this is nobelium. Nobelium, which made by heavy projectiles, when instead of the reactor, nuclear reactor, people use the accelerator and so on. A method was extended for the more heavy elements up to 106, seaborgium. And at that time was found an interesting thing, that maybe a nuclear matter is not like a liquid drop. It's not amorphous matter. Maybe it has internal structure. This internal structure make a difference. Some of nucleus are more bound, some of them is less bound, and more bound nucleus, a physicist called a magic nucleus, with proton, magic against a neutron. If they have both proton and neutrons, it's double magic. And extended, I mean, this philosophy for more heavy, not known yet elements, they come to conclusion that maybe instead of limit, which was proposed Gamow, the limit is extended, and instead of such a washout, I mean, the nuclear matter, we have instead new island of the stability, which consisted with very heavy elements, very heavy, super heavy, which we called, and that is completely different view on the material world. So actually, after continent which consists from natural elements, then we have artificial elements around thorium and uranium, and then we have a sea of the instability, which is the blue color on this picture. But if we go far from the known region, we may find some island, maybe not one, maybe a few islands of the stability, which really extend, I mean, the periodic table drastically. How to prove it? So we have to sail to this island, this mysterious island, which is very far from known region, thorium and uranium. So we have to have a ship to make such voyage. Unfortunately, all ship which was known and what bring us new elements does not work for this task. The neutron capture is just limited, as you see, very close to the known nucleus. Light ions makes a halfway only. Very heavy ions, so-called cold fusion reaction, which was proposed in Dubna, make pass by. So actually, we need to change once again the approach, how to produce such a super heavy elements. The choice was made for very exotic species, like artificial elements, a target produced with high flux reactor, and very rare acid of calcium, a lot of calcium in the boat. But calcium contains an isotope, very heavy, 48 mass number, which contains extra 8 neutrons, and that is very much important to produce super heavy elements. So actually, actinide nucleus heavier than uranium and calcium-48 make a sense, and we come close to the island and really see such enhanced stability which is expected from the modern microscopic theory. Left side, calcium-48 projectile. This is come from the Dubna accelerator. Right side, target plutonium-244 from Oak Ridge National Laboratory, United States. And we want to have a fusion between these two nucleus to create a new one. This is accelerator at Dubna, Russia. This is high flux reactor in Oak Ridge. This is separator and the registration setup for super heavy elements made in our lab at Dubna. And that is a reaction when after the fusion calcium and plutonium-244, we form a new element with enormous mass, 288, which due to repulsion move to a head and to separator, and immediately the detector system show you all decays, 6 generations of decays. I mean, we find 10 families, this kind of the decay of super heavy nucleus. They gave us a new elements, 6 new elements. They got a new names, of course, and they make, which is more important, 52 new atoms, extremely rich in neutron, and some of them has a half-life, not this microsecond, which was before, 30 hours, days, or maybe a few days. So actually, you see, the last we complete, 7 row of periodic table until element 118, and I would say a 50-year heavy ion odyssey from nobelium to element 118 led to discovery 17 new elements. So actually we made the bridge from known region. This is green light by cold fusion reaction and the hot fusion reaction to the island of the stability. The conclusion is that it's not the end. It's not yet the limit. There may exist a nucleus heavier than 120 with mass number more than 300. And the conclusion is when we leave a natural element heavier than of bismuth and go to the site of the more heavy elements, we see an impressive extension of nucleus variability. In this respect, the fundamentals of the modern theory concerning of the mass limit of the nuclear matter have obtained experimental verification. Okay, but in this site, we got the answer, but now we got also the problem. The discovery of super heavy elements poses many unexpected problems, like where is super heavy element located at the periodic table? Are they similar to the halide homologue? Where is the boundary of the periodic table? And this is another interesting moment. Then when we go to the more and more heavy elements, the electron velocity and the internal orbit become to be higher and higher. When it approaches to the velocity of light, according to the theory of relativity, the mass of electron will increase. This mass increase may change orbit structure. They make a so-called, relativistic compression. And in this compression also change the binding energy of outermost electron, which is responsible for the chemical properties. Now, for these super heavy elements, we have a question. Does element 118 look like a noble gas? And if you look at the literature, there are many articles now in publishing this year that most of them say, maybe not. Maybe it's not at all the gas. So actually, we have to continue. But to continue this, we have to really, again, come to modification of our setup. This is the right side with the indonone. The next is new one, which we want to produce now with new setup, because the production of element 118 is not the last, 119, 120, 121. After 121, there is two scenarios of continuation of periodic table. One is the new superactinide series, but another one could be really continuation of 8th row, but at that case, the group difference will be greatly disappear. We will wash out. A new facility, which we called Super Heavy Element Factory, was established at Dubna Laboratory. It is, after 2017, was equipped by new accelerator. So the life is continuing. Again, the problem, so many people are involved in this research. I just show you the laboratories in the world with him we're collaborating. Having today as a prize, I want to say you that you make a prize not only for me, but all for these people who was involved. Thank you very much.
Thank you very much, Professor Oganessian, for your presentation, which has brought us through the most exciting parts in humankind and the advancement of knowledge. Thank you for taking us down the trip to the new periodic table of super heavy elements and isotopes so essential in our world today. And thank you too for the discoveries of heavy metals which influence our life in more ways than one today. Excellencies, ladies and gentlemen, I have great pleasure and honor now to invite Professor Alexander Sergeyev, who is the president of the Russian Academy of Sciences, to address the ceremony. Thank you, Professor Sergeyev.
Уважаемые
honourable laureates of this first Mendeleev International Prize, dear guests, it is a great honour and a great joy to be here before you to say a few words about how in the Russian Academy of Sciences we perceive this prize. First and foremost, as some speakers have already said, the prize was established last year, which was a special year because it helped us to advance our work with regard to basic science. And it was almost also a wonderful year in the sense that, as I said, we founded the prize that year. Now, this happened when we launched the year of the periodic table, in Russia at the time, the president and the leaders in Russia decided that Russia and UNESCO would establish this Mendeleev International Prize, and I'm very grateful to the Russian government and to the Ministry for Culture and Science, represented today by Valery Falkov, for their excellent work over the past few years. It is through this work that we have been able to make the prize a reality. Now, of course, our colleagues here present at UNESCO have also made a valuable contribution, and this prize demonstrates that we, in working with UNESCO, are able to really advance the basic sciences. Now, I remember some famous words by Galileo, who said that the book of nature is written in the language of mathematics. Now, all of us here today, I think, might be able to argue with Galileo and say, no, the book of nature is written in the language of chemistry. It's true that if you consider the contribution of our two laureates, we might say that one of them, Professor Oganessian, has really made a unique contribution to the alphabet, so to speak, to the letters of chemistry. And our other laureate, Professor Balzani, works in creating words using those letters. Now, these are very interesting and beautiful words. And what we've seen today in terms of photochemicals and molecular machinery really demonstrates this beautiful description in the book of nature in the language of chemistry. On the other hand, of course, even after listening to today's excellent lectures by our laureates, we could say, no, but look, there's chemistry and physics, sure. But there's also, of course, not just the language of chemistry, but also the language of physics. And as Professor Oganessian said, the nucleus of heavy elements is created in interesting ways. There are various complicated effects involved. And we can see how long will the periodic table continue to be developed for? How long will it go on? And we can see here we have a symbiosis between chemistry and physics. Professor Balzani talked about how light is involved with the dissociation of molecules and how light can be used in relation to the molecular machinery. Now, that's physics. So truly, we can say that in some sense it doesn't matter in what language the Book of Nature is written. What matters is that scientists continue to pay attention to nature and to collaborate with nature in working on the basic sciences. We've said much today about the role of the basic sciences. And I think we all do understand how important the basic sciences are today for developing technology. We live in a fast developing world, and we're seeing competition between countries that is based to some extent on the owners of technology that originates from basic sciences. And those countries that are able to get basic scientific knowledge quickly and then produce market products using it, for example, medicines, well, these countries are really world leaders these days. But on the other hand, we also know that basic science has true colossal significance in the development of education. When we wonder what to teach young people in today's contemporary society, that is in a society that's changing very quickly as technology changes, of course. It's clear that our young people need to learn about the basic sciences because they're linked to technology, and technology is developing because of the developments in the basic sciences. The basic sciences are also part of culture, and contemporary cultured people also need to have more and more knowledge from the basic sciences. We've seen that all of this falls, of course, into the work of UNESCO, this wonderful organization that brings together education, culture, and science. I think it's very interesting and symbolic that today's event, it seems, is a sort of prologue to the upcoming year, which we hope will be declared the Year of Basic Sciences. That's very important for us because here all together we can see that there are many interesting initiatives that were developed in 2020. That's proof of success, and I think that in upcoming years and next year we will also have many excellent proposals to make, and consequently it would be great to celebrate the Year of Basic Sciences. I hope that the event taking place here today can be seen as a demonstration of our readiness to continue to develop the basic sciences. I speak in the name of the Russian Academy of Sciences and in the name of Russian researchers. I'd like to say that we are truly willing to continue to work with you so as to extend the field of the basic sciences and to help the basic sciences have an ever greater influence on culture, science and education. Once again, many congratulations to today's laureates. Thank you.
Thank you very much, Professor Sergeyev, President of the Russian Academy of Sciences, for addressing us here tonight. Ladies and gentlemen, excellencies, we've now come to the conclusion of this ceremony here. I believe we are all overwhelmed with the impressive ceremony celebrating science as humankind's greatest enterprise. We will certainly cherish in all our minds the examples and the words of these two exceptional personalities, their paths towards the advancement of scientific knowledge, influencing future generations, and really influencing science in enormous ways for all of us, and changing our world and our understanding of science. Allow me to thank you all for joining us today, for participating in this celebration, and once more a big hand of applause to our two laureates. Excellencies, ladies and gentlemen, none of this would have been possible without the support from the Russian Federation. And I want to sincerely thank them on behalf of UNESCO, on behalf of scientists across the world, for laying the foundations and good examples of advancing the basic sciences for our development challenges today. I thank the Russian Federation for this visionary initiative, commitment to this prize, commitment to the legacy of Dmitry Mendeleev, but commitment to our future generations to want our science, and the commitment of the Russian Federation to the role for basic sciences in meeting our development challenges today and for the future. I thank you sincerely, and thank you for joining us here tonight. Thank you very much.
Under my thumb, her eyes are just kept
Kiss me once, then kiss me twice, then kiss me once again. It's been a long, long time. Haven't felt like this, my dear, since I can't remember when. It's been a long, long time. You'll never know how many dreams I dreamed about you, or just how empty they all seemed without you. So kiss me once, then kiss me twice, then kiss me once again. It's been a long, long time. Kiss me once, then kiss me twice, then kiss me once again. It's been a long time. Haven't felt like this, my dear, since I can't remember when. It's been a long, long time. You'll never know how many dreams I dreamed about you,